So in lecture 10, we're going to continue talking about UMVUEs, that is uniform minimum variance unbiased estimators. And we're going to talk about this so-called Cramer-Rao lower bound and how that allows us in some cases to find the best estimator, the UMVUEs. So we should start off with a real quick overview of some of the things we've been talking about, just to set this up nicely. And so our setup was that if we have, of course, our famous setup, we have some random sample from some distribution parameterized by a parameter theta. And we had a couple different things going on. So it's a couple different new pieces of notation. So we should just do a real quick recap. We had what was so-called the score, which I had denoted as either S theta or S theta of my random sample, because the score is a random variable, which is alternatively notated the derivative with respect to theta of log f theta of x of my random sample, my random x tilde. So this is basically the function. We take the derivative of log f theta with respect to theta, and then instead of the x's, we treat the x's as random. We plug in random x's. And I had denoted this as basically DLD theta. This is a little bit of an abusive notation. It's basically, we're thinking of DLD, the score is basically thinking of DLD theta as random. So score, which is why I like my notation DLD theta, is thinking of DLD theta as, let's go down, as random. Oftentimes you'd think of DLD theta as you have your fixed x's you observe little x1, little x2, little x3, and then you could change the value of theta. Here we're kind of thinking for a fixed value of theta. You could think of it as a function of the x's, and then we're going to pretend that those x's are actually the random sample, the capital X's. So it's just like thinking of this score of DLD theta, derivative of the likelihood, the log likelihood function as random. And our theorem, which we've now reviewed twice, but this is very notationally heavy, so I think it's good to review these concepts a couple times. Our theorem was that in expectation, the score is 0. So the expected value of the score is a random variable, is 0. And the second thing that we had talked about was the so-called Fisher information. Named after Sir Ronald Fisher, famous kind of statistician. And the Fisher information had various definitions. Let's say that the information from n samples about a parameter theta, so the Fisher information contained in n samples about a parameter theta, denoted in of theta for information, is defined as, and there are a couple definitions we can give. One definition is negative the expected value of d squared d theta squared log f theta of my random sample. We alternatively saw that, so this is negative out front because the concavity, this log likelihood function is concave down. So this thing will be negative, and we want the information to be positive, so we add a negative sign out front. This is variously, we had showed that this is, let me write this in green, that this is equal to, you can either think of it as the expected value of the score squared, or the expected value, the way I like to denote it, is DLD theta quantity squared, because you can alternatively think of this thing as d squared, the second derivative with respect to theta, as kind of approximately equal to the negative, whoops, let's not forget a negative sign, the negative expected value of the second derivative of the log likelihood. Again, here we're thinking about this as random. So it's basically like negative second derivative of the log likelihood function with respect to theta. I guess I need a 2 here for second derivative. And then we kind of treat that thing as a random variable. And so that's why the Fisher information is related to kind of concavity of the second derivative of this log likelihood in some way. This was actually a theorem. So these two equality points here were actually a theorem. And these theorems, I'm going to put a little star here because these theorems, they required a certain amount of niceness in my PDF F theta for the theorem to actually go through, and this is not a concern for exponential families. So for exponential families, all of this works out nicely. If we don't work with an exponential family, some of this might not work out so nicely. So that was the Fisher information. It somehow tells us about how much information is contained in our sample about parameter theta. And the other fact we had here, I guess we had maybe 2 facts. Let's call it fact I, was that the information from n samples is n times the information from 1 sample. So here we have info from n samples, and I of theta is the info from 1 sample. That's my notation. And we proved that. And then maybe the last theorem, just to remind you of all of this, just as a refresher here in the first couple of minutes, is that, what was our theorem? Okay, if we wanted to look at a transformation, so here's my fact 2, or theorem 2, is that if, let's say our parameter theta is some function of some other parameter, psi, let's say, so, or alternatively psi is a function of theta, then let me write this more generically. If theta is a function of psi, or psi is a function of theta, either way, we can relate the information. So if I have like a transformation of my parameters where we might run into this, maybe I don't want to know something about the mean, but I want to know something at the mean squared. If I know the information for the mean for one parameter, what do I know about a transformation of that parameter? And the theorem said that the information for theta is d psi d theta squared times the information for psi, or alternatively, the information for psi was d theta d psi squared times the information for theta. So we can go back and forth between them, and all it involves is the derivative of the functional relationship one way or the other, and then you multiply by the information. So the information is tightly related through this kind of square of this first derivative. So this allows us to talk about information of not only the parameter, but other parameterizations. And it's basically just a shortcut. You could derive this straight up, but it's just a shortcut. Okay, that's all review. And then at the very end of our lecture, we got to the kind of the crowning achievement here. And this theorem is called the Cramer-Rao lower bound. And that's a kind of a mouthful here. So this is typically denoted as CRLB, Cramer-Rao lower bound. And this theorem is the focus of the lecture today, given the title I had for the lecture, and is going to relate to finding this best estimator. It's going to allow us in certain cases to find the best estimator. So what's the theorem? The theorem says that if I have my setup, I have some random sample. It's from some distribution f theta, parameterized by parameter theta. And let's say theta hat is unbiased for some function. We're going to write this kind of generically. You know what? Let's write it in two versions. Let's just write this in two versions. This is going to be simpler, right? Okay. So let's just say it's unbiased for theta first. If xn comes from this distribution, theta hat is unbiased for theta, then the real short way to write this is that the variance of any unbiased estimator for theta must be bigger than or equal to 1 over the Fisher information for theta. So that is kind of, let's call this version 1 of our theorem. Really simple. So this thing here, this lower bound, is called the Cramer-Rao lower bound. So that 1 over the information number is called the Cramer-Rao lower bound. It is a lower bound for the variance of any unbiased estimator for theta. So if you have any unbiased estimator for theta, it cannot have a variance lower than that. It is the best possible we can achieve. That's awesome. All right, that tells us about how efficient, how amazing, how great of an estimator we can get. There's a limit. You can't have a perfect estimator, right? A perfect estimator would be, it has 0 bias and 0 variance. You can make it unbiased. You can drive the bias to 0, but that puts limits on what your variance can be. The variance is not allowed to dip below this number. Version 1. We can generalize this to, say, let's call Mark II version 2, which is just a little more general. If theta hat is unbiased for some function, tau of theta, so it's not unbiased for a parameter theta, but maybe we want like theta squared or log of theta or something like that. You can similarly derive this because all you do is you have to change what this information is. And then in this case, the variance of theta hat is just, there's a couple of ways to write this, but it is, the variance of theta is not smaller than d tau d theta, the first derivative of this functional relationship, squared over my information. Now, period. So let's take a step back. So if tau of theta is theta, we just get the first version. If tau of theta is more complicated, you have to take into account the derivative of this thing. Notice how this is going to relate exactly back to the second point here, right? This is where this is coming from, and that's exactly how you prove the second point. We'll hold off on this for a second. We're going to put a big kind of star here. This requires, let's see if I can spell requires a nice / regular is the phrase used, PDF f theta or PMF. So I'm just going to put a big asterisk up here, i.e. practically what this means for the course is it works for exponential families, not otherwise. So this is why, and this is really why, you've seen several theorems now that work for exponential families, because exponential families are nice enough, they have this kind of regularity in property, or they're nice enough that we can interchange integration and differentiation. And so these theorems go through and we get these nice lower bounds and blah, blah, blah. Awesome. That is why we care about exponential families, because it makes your life so easy. Exponential family, I know this, bam, 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 I know all this. You don't work with exponential family, all bets are off. It's a much more complicated story. we don't know. We'll talk about it. The next topic, we'll talk about what happens in those cases and what do we do. But this is really nice because it works out nicely for exponential families. And that's practically in the course. You just have to more or less memorize or convince yourself something's an exponential family. Typically, as long as the parameter doesn't depend on, as long as the support doesn't depend on the parameter, it's typically going to be an exponential family, and everything's going to go through. And that's probably pretty much every example in this course is going to go that way. So pretty much, as long as the support doesn't depend on the unknown parameter, it's going to be an exponential family, and all these theorems are going to go through. And so if I ask you, what's the best estimator here, you're going to be able to use the approach we developed today. So notice that, let's just put a dotted line here. Let's say proof of version 2. If you believe version 1, which we'll prove, but let's just, if you can prove version 2 from version 1, I just want to say that notice that if, if we say tau is some function of theta, so tau is another parameterization. Above we use like psi, but you could alternatively call it tau. Then the information, it's just a different parameterization of our PDFs. The information kind of contained about tau would be, according to our theorem, would be take a derivative with respect to how do we want to do this? Yeah, so let's actually do it this way. The information about theta, according to the theorem, according to the first version of this theorem, according to this version, is d tau d theta squared over, times the information for tau, right? And how does that work out? So what this is going to do for us is we can note that the information about theta is, the information about tau is the information about theta divided by d tau d theta squared. And so the variance of theta hat, according to version 1, is greater than or equal to 1 over the information for theta. Now, if we just want this in terms of tau instead we want to reparameterize things and just think of it in terms of tau, that would be 1 over this part, 1 over, of course, I n theta over d tau d theta squared equals exactly what we had, right? So the second version it just comes directly from our transformation theorem and from the first version. So it's actually, there's nothing mysterious about version 2. It's just applying the transformation theorem, and you might connect that yourself. Okay. So let me just make a couple comments and then we'll look at examples. I won't pontificate anymore. We'll just look at some examples of what this does for us. So just real quick, some comments. What do we want to say? Well, if, I guess the main comment here is that if I have an estimator, let's say an unbiased estimator, let's call it theta hat star for, let's say it's some function of my parameter, tau theta. So I want to unbiasedly, I want to estimate theta squared, let's say. or e to the theta, some tau of theta, and have some unbiased estimator for theta hat star, right? So what I mean when I say it's unbiased for tau of theta, I mean in expectation, theta hat star is equal to tau of theta, right? Let me just explicitly write that. This means the expected value of theta hat star is tau of theta. Okay. If I have some unbiased estimator for whatever function of a parameter I'm trying to estimate, maybe I'm trying to estimate the mean squared, and I have an unbiased estimator for the mean squared, and if I calculate that the variance of this thing, theta hat star, is equal to my bound, let's say just call it Crlb, my Cramer-Rao lower bound, oops, Crlb, then theta hat star is the uniformly minimum variance unbiased estimator. Minimum variance unbiased estimator. It is the best estimator. So the search is done. That answers the question. What's the best way to estimate tau of theta using an unbiased estimator? The best way to do it is to use that thing. It is the lowest variance, lowest MSE estimator. Why? Because it's unbiased. So if we're only working with unbiased estimators, checks that. And so it's the UE on the end here is unbiased estimator. Is it uniformly minimum variance? Yes, because it has a variance that achieves the Cramer-Rao lower bound, and there cannot be an estimator, an unbiased estimator, with a lower variance. The variance of any estimator, unbiased estimator of theta, has to satisfy this bound. It cannot be lower than that. And so we can find an unbiased estimator with that variance. There ain't anything better than it. There's no way to estimate it with a better variance or better MSE. So that's really cool. I mean, it allows us in all these exponential families cases, as long as I can find an unbiased estimator, which might be hard, but we can talk about it. We'll talk about it in the next couple lectures about how we do that. As long as you can find one, and if you can prove that it achieves the bound, you have a proof that that is the best way to estimate it. The second point here is that if an estimator doesn't achieve the Cramer-Rao lower bound, I don't otherwise know it's not the UMBUE. So let me address that. You might say, well, didn't we just say it's the UMBUE? So if I can prove an estimator achieves it, it definitely is. If it doesn't achieve the Cramer-Rao lower bound, I don't know, because it's possible nothing achieves it. All it is a lower bound. It's possible nothing ever achieves that lower bound, and the best estimator doesn't achieve the lower bound. So it is possible. So if affirmatively, if you can prove it reaches the bound, we're done. If it doesn't, you don't necessarily know if it's the UMB or UE or not. Maybe nothing ever. All we said is that these things, that there's a lower bound. Here's another lower bound, 0. Nothing has a variance lower than 0. Well, it's kind of a useless lower bound, right? Just because an estimator doesn't achieve 0 variance doesn't mean it's the best estimator, right? We don't, in the same way, just because it doesn't reach the lower bound, if we find an estimator with a variance higher than the lower bound, it might be the UMBUE, it might not. So this is called an issue of attainment, and more on attainment later, either this lecture or next lecture, depending on time. We'll talk about attainment kind of later. So if it does or it doesn't, then we don't know, because all you know is it doesn't achieve the Cramer-Rao lower bound. You don't know if something has to. We'll talk about situations where we know, where we can actually. Right, so graphically what we could say is that it's possible that the situation is like this, where you have like our estimator, and actually, let's call it the UMBUE. It's possible you have a situation where you have the UMBUE here, you have all other estimators which have a higher variance, so the y-axis is variance, and it's possible that you have like the Cramer-Rao lower bound down here. So it's possible that the Cramer-Rao lower bound, this would satisfy the theorem, right? The best estimator has a variance not smaller than the bound, doesn't ever hit the bound, but it's not smaller, and everything else is bigger than it. So this would be the UMBUE, even though it didn't actually hit the bound. Turns out, basically, for one parameter exponential families, not really an issue, but we'll talk about that later. But in general, you do have to be a bit careful there. Okay, enough pontificating. Let's just do some examples, because this is kind of what you're going to do on homework exams and practically the skill. So, example, our favorite Poisson example. So we have data that is Poisson from a Poisson distribution with some unknown mean or variance, lambda. And I'm going to propose an estimator. Let lambda hat be x bar. Okay? Now, what do we know? We've shown this before, is that lambda hat is unbiased for lambda. Because it's x bar. The mean of these things is lambda, right? So just as a recap of Poisson, the expected value of any of my xn's is lambda, but that's also the variance. So Poisson distribution is kind of the only discrete distribution where the mean and the variance are the same. I believe that's true. Maybe that's not true. But it certainly is true that the mean and the variance are the same for Poisson. And so not only is lambda hat, by way back in lecture 1, we showed that the expected value of x bar is the same thing as the expected value of any of the individual summands in x bar. So the expected value of my lambda here, or x bar, is just lambda. So it's unbiased. So lambda hat, we would say, is unbiased for lambda. And my second point is that we can actually calculate the variance of lambda hat. And the variance of lambda hat, right, generally we'd say it's sigma squared over n. Well, what's our variance? The variance over n, it would be lambda over n, right? That's the variance. Because again, that second part of that theorem we proved way back in lecture 1 or 2 was that the variance of x bar, and the variance of lambda hat in this case, is the variance of any of the individual ones divided by n. So that's the variance of it. We want to find the UMBUE. Now, you might have the intuition, which is that x bar is our UMBUE in this case. And now we can prove it. So let's calculate the Cramer-Rao lower bound. Okay? So B, my bound, is 1 over the information for lambda. And we had shown, I think several times in the last lecture, that the information for a Poisson, information from Poisson distribution, is n over lambda. So go back to the lecture. I'm not going to reprove it. We did this several times. If I have n samples from a Poisson, the information contained in those n samples about lambda is n over lambda. And so my bound is 1 over the information. That is, the more information I have, the smaller bound I have, the lower I can have variance. That makes sense, right? If I have more data, I have higher information, and therefore I can estimate better, so I have a lower variance, and so my bound decreases. So if we do a little inversion here, this gives me what? Lambda over n. So that's my Cramer-Rao lower bound, right? And I'm just using the fact from last time that we had already done the calculation for the information. So notice that the variance of lambda hat is equal to the Cramer-Rao lower bound. It achieves, so lambda hat we would say achieves the Cramer-Rao lower bound. Hence, it is the best estimator, UMBUE for lambda, period. Done. The best way, if you want to work only with unbiased estimators, the best way to estimate lambda from a sample of Poisson is X bar, which is really nice. It's what we'd want to use, and we have just proven it is the best thing to do in terms of minimum variance or minimum MSE. So super cute, right? And this relies on the fact that what I've shown is that it's unbiased and it has a variance that is as low as any other estimator can be. There is no other unbiased estimator with a lower variance because it hits the lowest variance possible. So this was my first point above when I was talking about this. This is exactly what we do. Find an unbiased estimator, calculate its variance, and we show the variance is equal to the bound, therefore it's the UMBUE. Let me write that down as steps, which is 1, propose estimator. That's not necessarily a trivial step, and more on that in future lectures. But if we have an estimator in hand, someone, the Lord comes down, gives us an estimator X bar and says, use this, then we can say that, so we have the estimator, calculate variance of estimator. 3, show variance achieves, pretend I can spell achieves, Crlb. 4, then our estimator is UMBUE. So this is kind of like practical homework advice here. Those are the steps you need to take. Typically, we'll give you the estimator, and I'll say what you have to do is you calculate the variance of the estimator. You'll calculate the Cramer-Rao lower bound. You'll show they're equal, and then you'll say, okay, it's the UMBUE because it's unbiased. I guess you have to show it's unbiased. Let's say propose unbiased estimator. I give you the estimator. I guess you'd have to show it's unbiased, calculate its variance, show the variance is equal to Crlb. Then you're done. Just say, so it's this UMBUE, right? Because there ain't an estimator for lower variance. This is like homework or test advice. So notice here again. Consider, just as an aside here, back to our Poisson example, consider here S squared, right? Which, if we go back, not the score, but this boy, right? Our sample variance. And recall that the expected value of S squared is the variance of any of our individual exponents is lambda, right? So we had said that the variance of a Poisson is also lambda. And so if you go back to, again, maybe lecture 1 or 2, we had talked about how the sample variance statistic is going to be unbiased for whatever the variance is. In this case, it's lambda. And so S squared is another unbiased estimator of lambda. All unbiased means is that in expectation, it gives us back lambda. Cool. And is S squared better than X bar? Now we have an answer. However, X bar is better at estimating lambda. That is better, I mean lower variance. It's got a higher probability of getting it closer, of being closer. That's supposed to read however. However, X bar is better at estimating lambda than S squared, since X bar is the best estimator. as we just showed. So now we have a way of actually picking, right? So I could, if before you took this course, if someone said, well, I have two unbiased estimators, I have lambda, I have x bar, and I have s squared. Which should I use? If you assume your data comes from a Poisson model, you should use x bar. It's more efficient, is the word we use. And we'll talk about that second half of the course. Efficient meaning basically has a lower variance. It's going to be more closer to being correct more of the time. That's one way of thinking about it. So that's really nice. Okay, I think we're just going to do some examples for a fair bit here. Let's do at least 2 more examples in this lecture. So our next example, and this will kind of fully take us through the 4 steps I wrote above. So let's see if we can write these down, these 4. So let's assume that our data, let's do this in green. Let's assume that our data comes from an exponential distribution with some unknown rate parameter lambda. So what you have to recall, and you don't have to memorize this for exams, I will give you kind of common distributions on exams like I did in 451. Honestly, I have to look up these things half the time, so I don't expect you to memorize them. It's not the point of the course. That was the point of probability. It's not the point of this course. Recall, for a exponential distribution, the expected value of any of my x events is, not lambda, that's Poisson, is 1 over lambda, and the variance of my x of n's is 1 over lambda squared. Okay, that's just a side fact. So step 1 is, so what do we want to do? Goal is obviously find the best estimator for lambda. That's our goal. Step 1, propose estimator for lambda. Okay. In this case, I'm just going to give it to you. Let's say lambda hat, or estimator for, and I always forget, I want unbiased. Unbiased estimator for lambda, right? Let's say lambda is x bar. Let's not do that. Let's propose an unbiased estimator for 1 over lambda. Let's make our lives a bit easier this time, because that's the expected value. So propose an unbiased estimator for 1 over lambda. That's going to be a lot easier. So let lambda hat be x bar, then the expected value of lambda hat is 1 over lambda. So lambda hat is unbiased for 1 over lambda. Let's not call it lambda hat because that's weird. Let me back up here. Let's just call it t. It's weird to have a lambda hat, my estimator for 1 over lambda, to be lambda hat. Let's just call it t. Okay, t, my statistic, x bar, whatever you want to call it, right? So x bar is my statistic. The expected value of x bar, or expected value of t, is 1 over lambda. It's unbiased, so it's unbiased. Check 1, we have proposed an unbiased estimator, and I kind of gave you the first guess at x bar. You'd have to show in homework it's unbiased. 2, calculate the variance of my statistic t. And we've seen this before. Variance of t is the variance of any of my x of n's divided by n, right? That was our theorem way back from lecture 1 or 2. The variance, we said, is 1 over lambda squared. So we get 1 over lambda squared divided by n. So it's 1 over n lambda squared. Okay. Step 3 is calculate the Crlb. So this is a little more involved because I really should be specific for unbiased estimators of 1 over lambda, right? You have a Cramer-Rao lower bound of a specific parameter or a function of my parameter. So in this case, what I want to say is I want to notice we're not estimating lambda, right? We're estimating a function of lambda. So you could call that tau of lambda. well, we're not, I'm sorry, is 1 over lambda, right? We're not estimating lambda, we're estimating a function of the lambda, 1 over lambda. So this is why, and probably seemed arbitrary or stupid in this theorems where I said, oh, what if we want to work on a function? You might say, well, why would we want to work on a function? Here's an example. We want to estimate the mean. We don't want to estimate lambda, we want to estimate 1 over lambda. So my tau of lambda in this case is 1 over lambda. And so I need to calculate the Cramer-Rao lower bound for 1 over lambda. A couple ways I can do this. Notice or recall, our theorem says that the information, let's just say the Crlb by our theorem, the Cramer-Rao lower bound is what? D tau d lambda squared over the information in n samples for lambda. So we got 2 parts to calculate. Part 1, which is our denominator, is we calculate d tau d lambda is negative 1 over lambda squared by some calc 1 calculation. So d tau d lambda quantity squared is 1 over lambda to the 4th. Seems right. And part 2 here. Part 2 here is I need to find I n of lambda. Of course, I can just calculate the information for 1 lambda, and we might have actually done this, but let's just redo it so we get another whack at recalling that one. I can just calculate the information for one sample and multiply by n. So this should be n times the information for 1. The information from 1 sample about lambda is negative the expected value of, you could write it this way, second derivative of log f lambda of an xn, something like that, right? I think we did this calculation last time, but let's just recapitulate it. So this is kind of a sub step here. We're just gonna box it in here, and we'll change color here. So first of all, f lambda of an x is what? Lambda e to the negative lambda x. I'm going to leave off, you could add this indicator that x is bigger than 0. However, because it doesn't depend on the parameter, it's not going to make a big deal. Log f lambda of x is then, of course, log lambda minus lambda x. I'm going to forget about the indicator. It doesn't matter. It's just going to disappear when I take a derivative. And so I need to basically take 2 derivatives, right? Let's continue. Let's continue down. I need to take some derivatives. d lambda log f lambda of x is equal to, that's 1 over lambda, and then that's just minus x, which means if I do my second derivative, I'm doing this fast because we've done this, is negative 1 over lambda squared. Okay. And let's just continue up here. We need negative, and now replace x with a random. So we need negative expected value of, instead of this, we're going to, well, let's just write it d squared lambda squared, right? What I said is that this information is like, you go from treating x as like just some number to treating it as random, right? So instead of little x, we'll have some x, some random variable x. So maybe this, where here our x kind of comes from a Poisson distribution. And so this is negative expected value of negative 1 over lambda squared, which funnily enough doesn't even involve x, so that was a big hullabaloo about nothing. So all we get is 1 over lambda squared. I went through that fast, but that's not bad. What we're calculating is the information, right? So what we said is the information contained about lambda in 1 sample is 1 over lambda squared. And so information contained in n things about lambda is n over lambda squared. And now we combine it to get our Crlb. We take the square of the first derivative, it's 1 over lambda to the 4th, And let's say B, our Cramer-Rao lower bound is d tau d lambda quantity squared divided by the information contained in n things about lambda. Okay, 1 over lambda to the fourth is our numerator, and denominator is n over lambda squared. Now, if I have not made any mistakes, which is never guaranteed, what do we get here? We get 1 over n lambda squared, right? We can cancel that lambda to the fourth with the lambda squared to get the lambda squared. That ends up in the basement there. So it's 1 over n lambda squared. That is my Crlb. So this was step 3. And step 4 is to say the variance of t, which is my unbiased estimator, is, so just say, so variance of t, which is 1 over lambda squared, 1 over n lambda squared, right? Yep, that's right, is equal to the Cramer-Rao lower bound. So t is the UMBUE for 1 over lambda. So you can almost always tack on this kind of 4, whatever. You always have to, like, it's unbiased for this 1 over lambda. It's unbiased for lambda. It's unbiased for 1 over lambda. It's unbiased for log of lambda, right? You have to kind of specify what you're estimating. In the same way, you have to specify what the Cramer-Rao lower bound is for. Is a Crlb for 1 over lambda. And this is the UMBUE for 1 over lambda. But that's you know, basically the homework and test question. Obviously, that was a little bit involved, so depending on the question on the homework or exam, I'll feed you various parts of this and ask you to complete the other parts, right? So that's practically how it's going to go. But basically, just to recap, it's super cool, I think. I have data from an exponential distribution. I want to estimate the mean of these exponentially random variables. You know, so I collect this data. Maybe it's wait time for, you know, some component to fail. And my light bulb's life expectancy is, I'm going to assume it's exponentially distributed with some parameter lambda. Lambda is my kind of, is my like failure rate. And what I do is I collect, you know, I observe some light bulbs. They take some amount of time to die. So I have n samples of these. And then I want to estimate, this is literally what's done, reliability. And, you know, when you get, you know, this light bulb rated for this many years, this is how they get it, right? So they assume it's kind of exponentially distributed. Then they say, you know, what's my, I collect the data, how long it takes the light bulbs to burn out, which are my x sub n's, and I say, give me an estimate. How long does it take, does this thing last? So I don't want to estimate lambda, I want to estimate the mean time it takes one of these to burn out, which would be the mean of one of these, which is 1 over lambda. And so I want to estimate this. What's the best way to estimate it? Well, what we showed is that if I look at x bar, let's look at t, I'm calling her x bar. It's unbiased for the quantity I want to estimate. This lifetime is 1 over lambda. Its variance is 1 over n lambda squared. And that variance achieves the Cramer-Rao lower bound. So it's impossible to get an unbiased estimator with a lower variance. Therefore, step 4, it is the best estimator. It's the UMBUE for lambda, 1 over lambda. And that's why, you know, it's like theoretical justification for why we do what we do. So this is nice. I mean, the way history actually evolved is people have been using these quantities for a long time, and this is a kind of theoretical justification for this is why is it reasonable to do what we're doing here. And it turns out many of the kind of nice familiar quantities are reasonable. Not always, but it's a nice kind of helps you sleep at night. You know, if you're up worrying about how to estimate the mean of exponential, this will help you sleep at night. We're doing something reasonable. Okay, what are some other fun distributions we have here? Let's go back to our favorite normal distribution. So let's say xn's are IID from a normal mu sigma squared distribution. And sigma squared is known. So why do we say sigma squared is known? We're assuming we know what sigma squared is, which might not be realistic, but it allows us to think of this as a one parameter family. It only has an unknown parameter, mu. So what we want is the UMBUE for mu. We want to estimate the mean. So I think we did this example before, but it might be worth reviewing how we calculate this UMBUE. Yeah, let's just do this one in full. We did do this calculation of the Fisher information, but it's probably good to go over a second time. And it doesn't take that long, and we have a little bit of time today. So we want to get a UMBUE for mu. What do you think the guess is? Whenever you're trying to estimate the mean of something, turns out that x bar, not always, but often, x bar is the way to do it. So 1. Propose an unbiased estimator of mu. So let's say x bar, that seems like a reasonable thing to estimate. The mean width is x bar. So if we let t be x bar, then the expected value of our t is mu. We've shown that to be true, right? And let's say so x bar is unbiased for mu. Step 2, what was my step 2? Calculate variance of t. Again, back to either lecture 1 or 2, variance of t or variance of x bar is what? Sigma squared over n. And step 3 is calc the Crlb for our parameter mu. Again, I'm going to do this relatively quickly. We did this example more slowly in the previous lecture. So we want to find bound. In our case, notice this is the nice case where tau of mu is just mu. We're not estimating any function of our parameter. It's just the identity function. We're not estimating anything fancy. And so in this case, our bound, of course, you could write it as d tau d mu over the information for mu. But of course, d tau d mu is just 1. D tau d squared is just 1. So, right? Because if you take a derivative of this thing, it's just 1, right? So in the case where we have an identity function, again, as I said, the two versions of that Cramer-Rao lower bound converge. They give the same answer. So we just need our information, then invert it. So let's get our information. In of mu is well, let's first okay, let's say this. It's negative. In fact, we want the information just for one sample because we'll just multiply by n. It's negative expected value of the second derivative with respect to mu of log f. Say f mu. That's our normal distribution of x, let's say, something like that. Here my x is generically just something from my distribution, from my normal mu sigma squared distribution. And so we have to go through this whole rigmarole. F mu is 1 over root 2 pi sigma squared exponential negative 1 over 2 sigma squared x minus mu squared. If you do statistics as long as I do, you'll have that thing memorized. Hopefully by the end of this course, you'll have it burned into your memory, whether you want it or not. So log of this PDF is, let's say, negative, oh boy, I'm going to skip some steps. You can verify this is correct. Negative 1/2 log 2 pi, that takes care of this 2 pi-ish part, minus half log of sigma squared. We'll leave it like that. And then we take the log and exponential, just cancels it. We go 1 over 2 sigma squared x minus mu quantity squared. So if you call this thing L, dL, d mu, It's just a bit of abusive notation. Typically, L refers to when we have multiple samples. But again, it's like a one sample version. And I'm lazy, the LDMU is quick to write. So, oh boy, I won't be lazy. Let's just make sure this doesn't get confusing. dd mu of this bad boy is, the 2 pi thing goes away. The sigma squared doesn't depend on mu. That goes away. And we get our constant out front. And we get a 2 down times x minus mu. And we get a negative 1 from the inner derivative, just some chain rule. So we get 1 over sigma squared x minus mu. And so the second derivative is we just get a negative 1 over sigma squared, right? Cool. Hence, the information about mu is negative the expected value of that thing, which again, really nicely, it doesn't actually depend on x. So the expectation is just trivially negative 1 over sigma squared, which is 1 over sigma squared. So that's real cute. So all of that is to say now, we can bring our bound down. It's just 1 over that, all the way down here. Okay, which tells us that Cramer-Rao lower bound is 1 over the information mu, which is 1 over n times 1 over sigma squared, which is sigma squared over n. Looks familiar? Step 4. Because, so this all depends on the fact that we chose our estimator correctly. Hence, the variance of t, or the variance of x bar, is, of course, sigma squared over n. That is equal to our Cramer-Rao lower bound. So x bar is the UMBUE for mu. There it is. So again, what we've shown now is that x bar, if you just estimated the mean of a normal distribution, you assume that the variance is known, x bar is the best thing to do. Super cool. I mean, it gives some theoretical justification for what we're going to do, right? Which is to use x bar to estimate the mean, right? But it helps you sleep at night. Okay. Let's look at another example. Here's a little twist. People may be able to see what I'm doing here. Let's assume we have data from a uniform distribution. And let us go through the whole steps here. So let's say that 1, propose unbiased estimator for theta. So what we want is, we want UMBUE for theta. So let's propose an unbiased estimator for theta. I'm going to tell you some facts. We might have shown this. So let T be my unbiased estimator. Let that be the maximum. And we can show, and maybe we showed this in 451, you might have seen this. One can show that the expected value of the maximum is not quite theta, but it is let's just say it's n over n plus 1 times theta. So the maximum slightly underestimates theta. It is not unbiased for theta. So let's actually amend this. Let's just instead fix this, and let's make it an unbiased estimator. So if I instead let t be n plus 1 over n times the maximum, then we will get t to be unbiased because for theta, because this is n plus 1 over n times the maximum, which is n plus 1 over n times the expected value of my maximum. And I've just chosen, just multiply by a constant to make this thing unbiased. It's n plus 1 over n times n over n plus 1 theta is theta. So t now, which is basically an adjusted version of the maximum, is unbiased for theta. So that's step one. We have an unbiased estimator for theta. Okay. And I'm gonna, again, because it's just a 451 problem, but I'm gonna tell you a fact. Calculate. Our second step is calculate the variance of t, and in this case, the variance of t is, and I'm gonna spare you the details, but it's theta squared over n times n plus 2. And this is basically, my details is 451 calculation. Or an order statistic calculation. It's just some integration. It's actually not so bad. You can show that, so t has basically some beta distribution, or it's related to a beta distribution. And so that's where you're going to get that variance from. And I think if you took 451 with me, I would have actually derived that beta distribution in one of the very, very last lectures. Anyways, you can show that the variance of this thing is theta squared over n times n plus 2. Cool. Okay, so step 3 is Crlb. All right. So let's go through the steps. All right, f theta of x. You might say it's, f theta of x is 1 over theta for 0 less than x less than theta. And so you would say log f theta, maybe that's like negative log theta. Cool. Now I ignored this support earlier, maybe I can ignore it now. So maybe it's like negative log theta. So if I take the first derivative of log f theta, I will get negative 1 over theta, which funnily enough brings us back almost to our original thing. And if I do, so this is kind of our implication chain. If I take a second derivative, that would be like 1 over theta squared, right? So already this is looking a bit weird. Let's actually, the other way we can calculate our information, let's try this problem, and you'll see why I'm going to do it this way, is that the information for theta is, we could calculate as the expected value of the score squared. You notice when I took that second derivative, I no longer had a negative sign, which is weird because typically when we were doing it in our previous problems, you had a negative sign when you took a second derivative, and that canceled this negative sign, so something weird's going on. What's weird going on? We could calculate the information as the score squared, right? In this case, so that's the expected value of this thing, negative 1 over theta squared, right? So that, this is basically the score. It doesn't depend on x as it happens, and so this would just be 1 over theta squared. And so let's say Crlb, let's add a question mark. There's some weird stuff going on, we're not really sure. Of course, our implication is that the information for n of these would be multiplied by n, so it would be n over theta squared. And so the Crlb should be 1 over the information, the n information for theta, which is the inverse of this, would be theta squared over n. So step 4, question mark, what are we noticing here? Notice that the variance of my estimator, T, all right, so T is this unbiased estimator we derived for this uniform distribution. And it's unbiased, and its variance is theta squared over n times n plus 2. That's totally correct. And then we had this Cramer-Rao lower bound, which is supposed to be the lower bound for any unbiased estimator. But notice that the variance of my T is lower than the Cramer-Rao lower bound. So I have just developed an unbiased estimator that achieves a variance lower than the Cramer-Rao lower bound. How is that possible? It's possible because the theorem doesn't apply to the uniform distribution. I didn't break math, the theorem doesn't apply. Remember I had that asterisk in for the theorem that said we need regularity of the PDF. This needs to be an exponential family, a one-parameter exponential family is basically the answer. Uniform is not exponential family, right? So what should be setting off alarm bells when you do this calculation? You know, how do we deal with the fact that the support depends on the unknown parameter? That's not an exponential family. Notice here that more concerning things is that if I take my second derivative, that was 1 over theta squared, right? And so that's not equal, right? So you get a weird sign issue. So negative the expected value of d of this thing, which should be the information, is negative 1 over theta squared. Huh? The information is negative? That's supposed to be equal to this, which is positive 1 over theta squared. That theorem does not apply. It's not an exponential family. The Cramer-Rao lower bound does not apply. It's not. It doesn't have enough regularity. The PDF is not nice enough. It's too complicated. The support of the distribution depends on the unknown parameter. And so it doesn't apply. None of this applies. Of this applies because this uniform distribution between 0 and theta is not regular enough. Basically, it's not an exponential family. And that's the story. So that's why we're getting all these weird things. And that's why you can find an estimator with a variance that beats the bound, which shouldn't be possible. If the bound is the bound, you shouldn't be able to beat it. Well, it's only the bound for nice enough families of distributions for exponential families. So we're gonna kind of call it here, I think, because this is a nice stopping point. So this is basically the punchline for this whole thing about score, Fisher information, and how it's related to the variance of unbiased estimators, and how you can use it to find the best unbiased estimators. Next time, we're going to talk about a couple situations. We're going to go through some proofs of this, so it'll be a pretty theory-heavy lecture. This lecture currently will prepare you for the homework and exams nicely. Next will be a pretty theory-heavy lecture. We're going to prove some of the previous theorems. It's not that bad. This is a pretty straightforward proofs. It's some fun. And we'll talk about how do we know if the procedure is going to work, right? So we guessed at these estimators, and we got them to work. How can we be sure? So we had basically the second point. If we go way back up to my theorem here, let's go way back up. So we talked about this first point today. Next time we're talking about, quote, attainment. How do we know if our estimator is actually going to attain the Cramer-Rao? So we have kind of three situations. One, we find an estimator that is equal to Cramer-Rao. That means it's the UMV-UE. Two, the theorem doesn't apply, in which case, as I saw in this last example, you could have an estimator that beats the quote bound because the theorem doesn't apply, the bound doesn't exist. And the kind of third thing is this point here, this point 2 here, which says that what if I find an estimator that doesn't achieve the Cramer-Rao? It's a little higher. Do I know if it is UMV-UE or not? And we'll talk about that next time. And then we'll talk about, okay, what about non-exponential families? Basically, for non-exponential families, how do we determine what the best estimator is? And generally, the procedure we've laid out today, the first step, which is, you propose an estimator, right? I propose an unbiased estimator. Now, often I'll give you that, say an exam or homework. What if I don't? Is there a mechanism, is there a way to build that? And it turns out there is, yes, there is a way. And it will relate back to our talk way back about sufficiency of estimators. And so a nice kind of full circle there. Okay, but that's enough yabbering from me, so we'll call it there.